Assalamualaikum warahmatullahi wabarakatuh. A very good morning, good afternoon, or good night. So this is course Thermodynamics 2, EMM 3214, Group 1 for semester 2, 2020-2021. This is going to be assignment number 1, group assignment number 1 for this course. And we are from group 21. My name is Muhammad Sharifuddin bin Shafri. My metric number is 204304. And with me in my group is Lingeswar Analalaki Murugasu, matrix number 203701, and also Muhammad Irdin bin Muhammad Nazri, matrix number 202456. So in this assignment, we have this question that we choose from this assignment, that is to design a gas power cycle for internal combustion engine that is suitable to produce network output in a range of 500 to 600 kilojoule per kilogram. So that is going to be our W net. And then we would like to also calculate the backward ratio, BWR, efficiency, the temperature and pressure for each point in the cycle using both assumptions of cold air standard assumption and also air standard assumption. And then we would like to compare the results and discuss the difference between using those two standards. And we will also include the drawing of PV and TS diagram of the cycle. So the cycle that we have chosen is going to be the Brayton cycle, the ideal Brayton cycle, with some of its parameters, initial parameters given or decided. So we will move on to the next part, that is, as usual, before we solve any power cycle problem, we would like to first see the diagram for PV and TS. And for that, I would give this explanation to Muhammad Irdin. Please.
Okay, for the diagram part, the first part is cool air standard assumption. We choose the T1, which is inlet for the cold air standard assumption is 325 Kelvin. For this part, the bottom corner, this is the isentropic process. As you can see, the value for both assumption is slightly different. As you can see here, which is 43.3, the temperature is 1821.5 Kelvin for cool air standard assumption. But for the air standard, the value is slightly lower, which is 1657.5 Kelvin. For the pressure part, both assumption is the same value, which is the 0.1 and 4 for both part is 120 kilopascal. For 0.2 and 3 is 1200 kilopascal. We also choose the parameter Q in, which is equal to 1200 kilopascal for both assumption. The difference in value, as you can see here, will further explain in the calculation part that will be explained by Sharif and Inges. I think we go to the next part.
All right, thank you, Irdin. So I'm going to explain for the calculation of the temperature and also the pressure at each point. For the cool air standard assumption. For the cool air standard assumption, we will have the K value equal to 1.4. So the given values, this is the value that we decided, that we designed for the gas power cycle in order for that the cycle to produce work net equal to in between 500 to 600 kilojoule per kilogram. So the pressure ratio, we decided it to be equal to 10. And then the temperature at the compressor inlet equal to 325 Kelvin. So K equal to 1.4 for cold air standard assumption. And then the pressure inlet going to be 120 kilopascal and the intake of heat energy or Q in is equal to 1200 kilojoule per kilogram. So we would like to find the backward ratio, efficiency, temperature and pressure at point 2, 3, and 4. Okay. So if we look back at the diagram as before, process 1 to 2 is an isentropic process. So we can use this equation T2 over T1 equal to P2 over P1, where to the power of K minus 1 over K. And by using the given values of P2 over P1 equal to 10, we can get the temperature at point 2 equal to 627.7 Kelvin. And then by using P2 the relationship of the pressure ratio equal to 10, P2 over P1, we can get P2 equal to 1200 kilopascal by multiplying 120 kilopascal pressure 1 with the pressure ratio equal to 10. Okay. So we will have pressure 2 equal to 1200 kilopascal. And also note that pressure 2 is equal to pressure 3 and pressure 1 is equal to pressure 4 because this is Brayton cycle. And then we will use the information Q in, which is a process at from 2.2 to 2.3 that is constant pressure heat intake, and the amount of heat we're going to put in this cycle is 1200 kilojoule per kilogram. So Q in will be equal to H3 minus H2, but since this is cold air standard assumption, we can use the formula Cp multiplied by T3 minus T2, and then we put in, we substitute the number Q in equal to 1200, Cp equal to 1.005, and T3 is the temperature that we would like to find. T2 we just found it was 627.4 Kelvin, and T3 is equal to 1821.50 Kelvin. And then go to process 3 and 4. Process 3 to process 4, point 3 to point 4 is a process isentropic process. So we can also use the isentropic equation P4 over T3 equal to P4 over P3 to the power of K minus 1 over K. And we also note that P4 over P3 is equal to 1 over 10, the pressure ratio inverse. Okay. And then substituting the numbers, we get temperature at point 4 equal to 943.44 Kelvin. Okay, next, after we find all the temperature and pressure at the points 1, 2, 3, 4, we will find the work compressor and work turbine. Work compressor is 0.122, so we have H2 minus H1. Using equation for cold air standard assumption, we will have work compressor equal to 303.98 kilojoule per kilogram. And then work turbine 0.3 to 0.4 H3 minus H4. So substituting the number, we get 882.45. Backward ratio is equal to work compressor divided by work turbine. 303.98 divided by 882.45, we get 0.3445 or equal to 34.45%. Backward ratio means that we use 34%, 34.45% of the work from the turbine to turn on to put into the compressor. Okay, the higher the number means the more energy we need from the turbine to operate the compressor. And then we have the thermal efficiency equal to work net divided by Qn, and work net is just equal to work turbine minus work compressor, which is 578.47 kilojoule per kilogram work net. And then 578.47 divided by Qn 1200, we have 48.21%. So that means that this cycle is 48.21% efficient. Right. So next would be the air standard assumption explained by Lingus.
Okay, thank you, Sharif. Okay, I'm going to explain about the hair standard assumption. Okay, so from the given value, we can take that the pressure ratio RP is equals to 10, the temperature at the compressor inlet, which is 325 Kelvin, and the K is now the K is not equals to 1.4. where we assume all this value from the table, the pressure table. Okay, so the pressure inlet it is 120 kilopascal. So Q in is 1200 kilojoule per kg. So now, okay, from the table A17, so we can get for the temperature 325 Kelvin, we can get the PR1 1.8345, and the enthalpy H1 is 325.31 kilojoule. From there, we can from using the RP, I mean the PR, the RP, the pressure ratio, we can assume that we can get the pressure 2 over pressure 1 is equals to 10, which is equals to PR2 over PR1. From there, we can find the PR2, which is 10 times of PR1. So we can get the value 18.345. So from the table A17, we can do the interpolation for PR2 18.345 to get T2. So from there we interpolate, we get T2 equals to 619.95 Kelvin. And for the enthalpy 2, we also need to do the interpolation, so we can get 627.9 kilojoule per kg. So from there, okay, for by using the q in given, which is 1200, we can find h3 by adding the q in and the h2 that we found earlier, which is 627.9. So we get 1827.9 kilojoule per kg. So from by using the enthalpy, we can do the interpolation to get the temperature at the point 3 and the PR3 at point 3. So where we get the temperature at point 3 is 1657.5 Kelvin, and the PR3 is 919.76. Now, so since it is same as it follows the where PR3 and PR4 occurs in occur isentropic. So we can find PR4, which is PR4 is PR3 over 10, where is 10 we divide by 10, so we can get 91.98. So from there, we need to do another interpolation to find the temperature at point 4, which is 947 Kelvin. So by using the ratio, the pressure ratio, we can find P2, which is 10 times of P1, where we can get the P2 is equals to 1200 kilopascal. Since it occurs in the constant pressure, where PR1 equals to P1 equals to P4, where P4 is equals to 120 kilopascal, where another thing is P2 is equals to P3 because it is constant. So P3 is 1200 kilopascal. So from there, by using the H4 and H1, we can find Q out, which is 660.49 kilojoule per kg. From there, we need to find a work net, so that the work net range should be between 500 and 600, which is given by the question. So we find work net by subtracting q in and q out. So we can get 539.51 kilojoule per kg, which is occur at the range that given. So from there, from that we can get all the pressure for each point and the temperature for each point. So after that, the question asks to find the back work ratio, which is we should use the WC, work compressor over work turbine. So from there, we can for work compressor, how we find the work compressor is H2 minus H1, where we get 302.59 kilojoule per kg. And work turbine we got uh, H3 minus H4, where 18 is 1827.9 minus 985.8, which is we can get 842.1 kilojoule per kg. So there we find the back work ratio, where we get 0.359, which is equivalent to 35.9%. So and then they asked to find the efficiency of the cycle. So how we find the efficiency? We find the efficiency by, yeah, by work net divided by q in. So where we found earlier the work net, which is 539.51, and q in that is given, which is 1200. So from there we can get 0.4496, which is equivalent to 44.96 percentage. So we can conclude that the back work ratio is 35.9%, and the efficiency is 44.96%. Okay, that's all from me. Okay, I would like to call Iridine to further this slide.
Yeah. For this is a table data for the calculation for the air for the cool air standard assumption. For the point one, we got our assumption, which is 325 Kelvin and the pressure of 120 kilopascal. For point two, the temperature is 627.47 Kelvin and the pressure is 1200 kilopascal. For point three, the temperature is 1821.5 and the pressure is the same as the point two, which is 1200 kilopascal. For the point four, the temperature is 943.44 Kelvin and the pressure is the same as the point one, which is 120 kilopascal. For the backward ratio is 34.45% and the efficiency is 48.21%. For the air standard assumption, point one started at the temperature 325 Kelvin. For the pressure is 120 kilopascal. For point two, the value is slightly different from the cool air standard assumption, which is 619.9 Kelvin. But the pressure is the same for the cool air standard assumption, which is 1200 kilopascal. For point three, the temperature is 1657.5 Kelvin. For the pressure is the same as the point two, which is 1200 kilopascal. For point four, the temperature is 947 Kelvin. For the pressure is 120 kilopascal, the same as the point one. For the pressure part, the value is the same because of the constant pressure, which is point one and point four is the constant pressure, and the point two and three you got the constant pressure. For the backward ratio for air standard assumption is 35.9%, and for the efficiency is 44.96%. Okay, for the value above, for the result above, the value for both assumption is slightly different, as you can see in the temperature value for 4.1, 4.2, 3, and 4 for cool air standard and air standard assumption. The value for backward ratio and efficiency is also slightly different. Although it's slightly different, the value calculated by using air standard assumption is more accurate than the cool air standard assumption. It is because by using cool air standard assumption, the assumption made is that the process is occur at 25 degrees Celsius. So it's not quite accurate to be used in real life application because the Brayton cycle usually occur in higher temperature, not at 25 Celsius. And second, by using cool air standard assumption, we use the constant K, which is equal to 1.4. The constant K is used when we calculating the isentropic process in the isentropic equation. But for the S standard assumption, we just use the thermodynamic table. We just find the value based on thermodynamic table. So the value for the thermodynamic table is more accurate than the constant. I think that's all from us. Thank you.
All right, that would be all from us. Thank you.
Thank you.